Does anyone have questions on the current project? It's due Tuesday, like 2 weeks from now, the 21st or something. I think it might be due after spring break. So any questions on that or the previous project? No? Okay. Well, before we get started today, we're going to do a little activity to get the presentation started. So we're going to give 15 minutes of class where you can just walk around and talk to someone for like 2 minutes. And we want you guys to like, for the 2 minutes you're interacting with that person, talk about your project ideas, see if you have like similar ideas or wants what you want to do in the presentation, and maybe you can find a group or just bounce ideas off each other. Right, so for like 10 minutes, you're going to be able to talk to different people and find out maybe cool ideas. So please, begin. Yeah, questions?
Yeah, please give us basically
ask what other people are thinking.
It was similar, but it was so I don't really have so much experience with that.
I think everyone should talk about your projects, find someone to talk to. Find someone and talk about your presentation, and then after 2 minutes we'll find someone else. I think it's like what? If you want to do it before, not against it. You have to keep in mind how much. So we'll say to you before there will be
Alright, everyone find a new partner. It's been 2 minutes, new partner. Walk around. Get up a bit, walk around.
Why do I have to? Are you making me talk to me?
I said it out. Really like that assembly.
No. See, I'm actually an initiator. She has sister. Yeah. 2 minutes 6. I was thinking
Fine architecture. That's just for the to make for a very good
Oh god, no. Dude. I don't have much. Yeah, I think I was talking to Steve about this. He said he was like, dude, I don't know. Because that shit's comment said that like GitHub.com / private. It was like someone who like posted it turned out to be like a troll. I don't think it was that easy.
The biggest refuges were gone, so she's gonna get here eventually. It's gonna be a while though.
All right, guys, one more. Swap around.
Exceeding this time, fifth grade,
Alright, so you two are gonna hack a camera, right?
Okay, everyone, one more time, find one more person to talk to. This entire half the room is just not moving. Come on, people, let's go. Especially you, let's go.
Tony, find graphics, I can see this.
Find someone to talk to.
I did! Apparently I'm here from my high school. I talked it down. I came up with ideas. I talked to like 5 people. Whatever that is. I think yeah, we're basically good. Yeah. Okay. Right, you can do it for the book.
You can only help because you got some more ideas.
Everyone has the same fucking idea. Everyone's like, I'm going to reverse an IoT because everyone's like,
Why no one knows how to do Okay, people, let's get back to the seats. Thank you. He's only hired. So, who wants to say an idea they talked about? Anyone? Yeah.
We were talking about reverse engineering the scanners of the dining hall.
Okay. People have done that. It's not for this class.
Yeah, so if you really can't do anything where you hack into a university thing, they will prosecute you. They will actually suspend you aggressively. Hold on. And there was a case a number of years ago where they changed the meal plans. I forget, this is so long ago, I forgot the details, but there was something like if you were off campus, you had to have a real off-campus meal plan, and people were upset about this. You could no longer just sign up. So the way the webpage worked is they would actually do the validation of, if off-campus must do this plan, if on, and so people figured this out, and someone posted to Reddit, since the validation is on the client side, you can just tell the server that you can have any meal plan you want. So a lot of people did this, and the university kicked them all out for a semester. And one of the students was at, did you know you used to be advised by faculty, not the advising center? So one of them was my advisee, and I went with the chair at the time, and I think, Dave Barrington, who was undergrad program director. And they were just absolutely not, we're kicking these students out. And we were like, what if they had gone into the main office and just filled out a form wrong and you messed it up? And they were just like, no, you can't have this. So do not mess with the university. They don't care. And if you want to mess with the university, though, I am good friends with Chris Misra, who many of you took 360 from. He runs the entire campus in terms of IT. If we tell him ahead of time, he may let you do that. Okay, so yeah, go ahead.
So Spire is off limits as buggy as it is.
No, that's serious. They will kick you out, and when you apply to grad school or a job, you'll have to say I was part of an incident. You might not get clearance if you want to work for the government. It's a big deal. So probably should have said this at the beginning of class.
Yeah. And just real quick before we continue download these files, the flags you need for GCC is in the C file filing too. Also on that, I think someone in the club a year or two before my time reverse engineered the doors, the scanners, for a Hack UMass project. I'm pretty sure they got in big trouble for that.
Oh, okay, good. I was going to say, don't tell me. But yeah.
But if you want to do a different door scanner,
yeah, you could buy a door scanner. If it's cheap, I'll buy it for you, that kind of thing.
Yeah.
What if we do it for another university's?
And law enforcement the criminal area. Let's just say if you get a door scanner that is not related to anything I know of, we're good. Or anything that you know of, let's agree with that.
Yeah, and also I'll say relatedly, this is a white hat class and the university. I am not teaching you to be hackers. And also, I won't defend you. I just gave you all a warning, and I'm going to be I told them, don't mess with, your, especially, also, I mean, do I have to go to town here? Don't mess with your roommates. Same deal, family. That's not okay either. I mean, if you did it to an ex, you'd probably go to jail. I mean, no joke, right? That at that point is stalking. So don't mess with anything. All you have to do is tell me what you want to do. We'll get you another copy of it. I would also not get a copy of things the university has. All we have to do is approach Chris Misra, get the okay, that kind of thing. Okay.
Other ideas?
We were thinking maybe getting an off-brand Fitbit from AliExpress that might have location data and might not be programmed very well, and dumping it and seeing if maybe we could send the location data to someone where it's not supposed to be.
That sounds like a good one.
Just something, this seems to be a bit of a pattern with the project so far. In this class, we don't really teach embedded or how to dump stuff from embedded devices or stuff like that. So unless you're already extremely familiar with it, getting that done and especially debugging it if it doesn't work out like you thought it might is a complete pain, and that could very easily lead to you not getting anywhere with your project. So I would strongly consider at least most people just choose some project that you can compile on your actual machine and to do tests there, because that's what we actually teach in this class, and that's what we're kind of looking for in the final projects. If a couple of people do embedded devices, that's fine, but it can go very wrong, and it adds a layer of difficulty to it that we just don't cover in this class. We can help you with it to a degree in the cybersec room and stuff, but it's not something we teach in this class specifically.
I could add on to that actually, because I did the exact same idea. So like,
He's in UCA, by the way, if you don't know.
so like, I had a camera and like, I was trying to get the flash off it. I got it off, but like, the camera never turned on again. I blew up like 2 cameras, and like one time I plugged it in and like popped like really loudly. Yeah, a lot of stuff can go wrong. Like I think I know a little bit about hardware too, but you know, there's things that can happen out of your control. So, but if you ever want to tackle, I'm your guy.
Yeah, like we'll have people that are designated like working for the class that will help you if you want to do hardware. That being said, we're not gonna let every group do hardware. Only a few will. So after class today, we'll release a form where if you have a group you want to work with, you tell us the members and 3 project ideas, and we'll choose a project idea for you so there's not too much overlap between everyone. And then for people that don't have a strict group yet, we'll make a campus wire room where people can talk and connect. And we're looking for groups of size 3 or 4, right? It's expected that everyone works equally. Does anyone have a non-hardware idea? Yes.
Trying to like reverse engineer some kind of ransomware or something and see if you can disable it without having to pay or do whatever they want.
Let me look up. Speaking of ransomware, I think it's called malware too. Yeah, there's just a GitHub account with like a bunch of malware. I'm not saying you should.
I think they just go for VX Underground for that.
VX Underground.
They have like the biggest selection out there.
But like, these are source and binaries of a bunch of different things. Please run this in the VM with Wi-Fi turned off. Don't run it at all if you don't have to, right?
Don't be connected to the UMass network while you run it.
We are not liable. You are. So keep that in mind. Yeah.
Any of that malware contain malware that allows it to escape VMs and break through?
You're using an updated VMware.
Yeah, but there's always a chance.
Yeah.
There's no 0 days in this, right?
Yeah.
If you're on the latest patch, no shot. But there could be, if you have an out-of-date version, there very well could be.
Yeah, and by the way, part of the problem is like you run this in the VM and then Windows is like, oh, this is malware, I'll just delete it for you. So you have to like turn off Windows virus checking in order to mess with this in the first place, which is why you have to use a VM. But then even then, it just gets on the network.
Yeah.
So be careful.
And now Windows is fun where if you turn off Defender, it'll just automatically turn it on for no reason because it just doesn't want you to do it. During the malware and obfuscation lecture, I'll actually show some tools that would like. So okay, raise a hand. Who actually watched the shellcode lecture? Okay, everyone should be raising their hand. But shellcode is like the beginning of like writing exploits, right? It's like injecting your own code into a program. There are tools where all you do is put the IP you want your malware to connect back to, and it'll write the shellcode for you. And it will automatically, import that into a Word doc. So if you click the Word doc, it'll do it. So we'll learn about stuff like that. But Windows Defender, if you use that tool and upload it on a Windows device, will instantly delete it because everyone uses it, right? So you have to be aware of that. All right, other ideas? Yeah.
The original Minesweeper from Windows XP.
Okay. And what do you want to do with that? Just reverse it, find out how it works?
Look, see if there's anything you could do with it. I don't know.
That might be a bit too simple.
Yeah.
Just pointing it out, it's like a project I did like on like a day last year at some point. I like uploaded a blog post to my blog at the time about it. It's like a very simple little binary. So I don't think it would be like suited as a final product for this, but definitely do it in your own time if you want. It's like very simple, very fun to put into for a weekend.
Right.
Yeah, but finding bugs in older systems is a good project idea too. Like maybe when we do program analysis in the second half of the class and you learn like tools like fuzzing and like automated bug hunting, maybe you just run that against a ton of Windows XP binaries and you just see whatever your automated tools can find, right? That could be something.
What else am I exploring the Zoom code base?
Sure. If you want to find a bug in
Is
Zoom,
that even C, C++?
that might, yeah. If it's not C, C++ assembly, it might be harder.
Because we are covering like memory corruption vulns in this class, so a lot of the stuff that you might find in a web app style application like Zoom is not applicable at all. But yeah, it's good that
Really
you
what you're saying is compiled code. Right?
Yeah.
pretty much, yeah.
You can, so anyone could download an app and then just run, there's a command called file in Linux that will tell you, do you want to run file code? That will tell you what kind of file it is and whether it's like all, I don't know, uncompiled interpreted something.
Something also to note is if you want to do Windows bug hunting, it's very different from Linux in terms of reversing. I'm about to learn a lot about Windows API, stuff like that. Keep that in mind. Let's hear one more.
You may be doing something with like arbitrary code execution in like a retro video game or like simulation.
Yeah. So things with
Is anyone just thinking about choosing like some open source project off GitHub and working from that? Has anyone had like thought about that, doing something there? Yeah, Eamon, what do you do?
There's a game client. There's the add-on for if you ever play Grand Theft Auto. There's a big add-on that's like used by 200,000 plus concurrent players called FiveM. It's clients written in like mostly C++ and a little bit of C. And I'm looking at like running some tools on once I compile it against it and looking for crashes and seeing where the crashes are and looking for bugs once I get crashes. And that would be a little bit harder because, like you said earlier, it's Windows, so it might have some difficult stuff with the Win API, I think you said.
Yeah.
That's a good project though.
Yeah, that's a good project. For reference, like finding bugs in open source tools, I don't want to say I don't want to say common, but it's like very doable. Like the same thing Eamon was just talking about. Eamon found a bug in the same program like a month ago, where you can just send a message to everybody on the server and get all their information, right? And it's like a web phone because it's the GTA has like a phone browser, right? So you can consider things like that. But yeah, we want you to do memory bugs in this class. So no web stuff.
Also, like so far in the course, pretty much all we've been doing has been like reverse engineering. So like so far, you're kind of like used to looking at Ghidron, but that's not what we're going to be doing. Like the entire rest of the course, pretty much going to be more open source. So I think this project is still closed source. But like second half of the semester, everything is open source, for example. So while reverse engineering is like very important in the first half, now we're going more into like how to actually exploit these bugs. After that, we're going to be more and more like open source stuff. So that's like very relevant to like this class.
Okay, I think now we will start the lecture. So, as a quick recap of the lecture that everyone definitely watched, right? What we learned is that if we have, actually, let me just pull up the actual slides. Okay, so what we've talked about is that with a program like this, where we have a buffer overflow and we have a pointer to the buffer, right? If we actually know where the buffer is in memory, we can overwrite the return address, jump back to the buffer where we previously written code. So right now we have, if we can write actual assembly code in memory to the program, given the buffer overflow or return address overwrite or anything that redirects code execution, we can redirect it to stuff we've written in memory, right? And then the computer doesn't know the difference, and we'll treat that as executable data and actually, trigger the opcodes. And then also as a side note, if you watch the lecture, we learned syscalls, right? So we learned, we can do assembly code, but it doesn't really matter if we can't do anything outside the program. So hopefully, we can now use the syscall opcode with data such as this to do read, writes for files. We can execute shells. You can spawn sockets and connect to other machines, right? So you can have the machine spawn a shell and connect back to you. All different things that, malware always uses, bug hunters always use. Very important stuff, right? So now we go to today's lecture where you have why is this not in presenter view? I hate Google. Right. So in today's lecture, we're looking at today's lecture, we're looking at this code, right? But now we don't have a memory leak to buffer, right? We have a huge overwrite, but we don't have a pointer to where our memory is. Can we get full code execution on this one piece of code? Right? Any ideas? People think about it for a minute. We can write stuff to memory, right, with fgets. Is there anything else we can do?
we have the shell code, and if we know where, so if we know where everything is in memory beforehand, we can probably jump to, since we have like 100 on the stack, we can jump to shell code above the return address.
But see, stack memory is randomized, so you don't know where stack
Yeah.
is. So we can't do that. Yep.
If you know where FKS is in the code, then you can like jump to any library function.
That's an idea. That's a good idea. So let's talk about that. Right. So just general things. We can corrupt the stack, right? We have a buffer overflow in this program. We have no pointers to jump to, right? Assume if you looked at the compilation flags that I gave you, the actual code for this file is loaded in the same memory location every time, right? I didn't put relocation on. So mains always go via like 0x40 something, 40,000. I don't know. But that's key for now, right? Oh, I hit buttons. So we know at least the actual code of the programs in the same place. We don't know where things are in memory, but we know the code. So this is the assembly of the function we were just looking at. If you open it in GDB on your machine, you'll see the same thing. And it's really short, right? And I'm telling you, you can get full code execution of this. So let's look at what it's doing. First thing we do, set up the stack, right? Second thing we do over here is we actually just get the fgets call, right? That's all this program's doing. And what we can do is we can corrupt all this data, right? I could write a how many times? 256. And we could just overwrite all this data. Note in this diagram I'm showing that these bottom three are the current function stack, and we're actually overwriting old function data here, right? The function that called main, we're overwriting the data for that. Okay? This is important because we're overwriting more stack data than this current function is using. Remember I talked about that previously with buffer overflows, that we could theoretically overwrite older functions memory, but we don't really know if that's useful. It could be. But this is key here. So we overwrite all this data. We can control the base pointer and the return pointer, but we don't really know what to set it to. Does anyone see something here now? Most likely you won't, but... Okay, so it looks like we need to go at once, right? We trigger the buffer overflow, and what happens after that, right? So now we're here. The leave opcode cleans up the stack for the current function, right? Because we're going to leave the function. So what it does is it adds back the RSP. We can see here the RSP now moved to return address. And it's going to pop the old base pointer. So now the base pointer is set to that. And last, we're going to use the ret opcode and pop the old return address, right? This may have been corrupted, but this is what the program's going to do regardless, right? All these values may be corrupted, but they're still going to pop it off the stack. So we can see RSP is now pointing to the start of the old function. Does this make sense for everyone right now? Right? This should have just been how functions work, except all the data is now corrupted. So what do we have control of here? Can someone tell me what we have control of? Assuming we can corrupt everything, even if it doesn't seem like it's useful, what can we control? Good hand up first.
Stack pointer.
Yes. Okay. So we could. Well, actually, let me rephrase. Not the stack pointer, because that's only moved by pops. But we could have changed the base pointer to whatever we want, right?
Yeah.
Which is one of the stack pointers. What else? Yeah.
Yeah, the return address.
Okay. So we set the return address to anything. But do we have anything that seems useful to point to right now?
Another buffer, the older buffer, or like.
Well, we can't point to the buffer because that's a memory. You don't have memory locations, right? If we had, say we had like a move RSP to the instruction pointer, then it would be useful,
Yeah.
but we don't, right? So it doesn't really seem like we have access to anything, but let's take note of what we currently control, right? The return we control, and let me get a butterfly grid. Yeah, so we control the return pointer and the base pointer. Okay, so let's go into some theory. Is this exactly what I just said? Right? So what we can usually do is we can, if we wanted like old buffer overflows, we could send the return pointer to another function in the code, right? Well, I didn't give you another useful function. The only thing that's in here is fgets, and that's it. And with global Stack Overflows, or sorry, not Stack Overflows, shellcode, we can write our own code and we can jump to that, but we don't have anywhere to jump to. Okay, so clearly both these methods aren't going to work. What we do have control of, like I said, is the return pointer, the base pointer, and maybe we kind of have control of the stack pointer, right? What we could redirect to, like if we just look at the main code. So technically what we could do is we could just always jump back to main, because we know this is loaded at a constant place in memory for now, right? This is always at 40,000 something. So we could keep hitting this return opcode, and every time we call return, the stack pointer is popped, right? So that might not be useful, but if we look at our diagram, every time we do this, RSP will keep moving up, okay? And then there's other opcodes we could hit. We could hit leave, which will subtract a lot from RSP, and if there's any pushes, say we jump to the start of main, we could actually move RSP down, right? So we control the stack pointer. Maybe that's useful. So let's add that to our list. Okay, and just to actually prove we can do this, right, we're going to write a script. What did I call this? Red example? Nope. It's one of these. Yeah, okay. So we're going to start the process. Let me make this bigger. Do the payload. Send the payload. And then interact it. Actually, let me run the other one. I have one that has... Yeah. Okay. So I pre-wrote this just to make it faster. But what this is going to do is going to spawn GDB so we can actually debug stuff, right? I have the proper amount of A's, so we'll actually get to the instruction pointer. And this payload should jump us to return address. So if we GDB, the actual program, and we break main, disassemble it, we can check this out, right? So the address I have here adding to the payload corresponds to the return address, right? So does everyone understand when I say if we run this script, let's just go hit return. We're going to overwrite the RIP as return first, right? So let's actually test that out. Okay, so all I did is the code breaks right before main is going to return, okay? It already sent the payload, it did the overwrite for the RIP, and we're breaking right before main. As we can see, if we step one more, it's going to jump back to the same opcode, right, return. Does this make sense? So we're going to step once, and you can see it's going to jump to main again, right? So we can continually ask it to jump to main, pop the next value off the stack, which is just going to be the same value again, because we can corrupt all the way up as we want. And we can continually call ret. Right, I do it again. Let me actually relaunch it, and we'll actually look at the stack this time to see that it's popping values off the stack. So we can see we already left, so RSP should be pointing to the return address, and that is currently pointing back to main. Okay, and if I do examine RSP -8 +8, the same value's there, right? So if I examine RSP +8, it's the same. If I do RSP +16, it should be the same because we wrote it 3 times. Let me draw a diagram. This might be a little easier to follow. So, current stack. This code is old function, right? This is main. This entire area, this is the return address, right? This is the base pointer, and buff. What we're doing, all of this, we're setting to A's, right? Just trash. Then we're going to overset the base pointer, also like these, right? We don't really care about the base pointer set 2. Then return address, let's say this address is at 0x10, right? We're going to put 0x10 here, and then here, and then here, right? So when the function returns, we get rid of this because we don't need the stack anymore, and then we're going to pop return address, right? And the code's going to go to whatever this return address is, but we overrode it to 10, right? So it's going to go back to the instruction for return. We can keep calling return. Is this making sense? Yes. Yes.
Does that cause like an infinite loop?
Well, it only will do this as many times as I overwrite return.
Up, right?
Right, yeah.
Okay.
Because every time I pop the current return address, the stack pointer keeps going up. So if I have another color, every time, so the first leave, right? The first leave instruction gets us here. This is leave. And then this is return 1, or sorry, leave gets us here. And then return 1 gets us there. Return 2 gets us here. And every time we call return, it'll pop us up one more. So eventually we're going to run out of how much we go over. And then it's going to be trash. And then the program will probably crash. Right? I can actually probably hit continue and the program will crash. Did it say fault? I think I did it one time. Maybe one more time. It should say fault. Yeah, invalid address, right? Because I wrote, just to say when we're done with the returns, I put some random value, and eventually it'll say fault. Any other questions? Yeah.
How do you get out of that, like, returning over and over?
We don't know. We just know that we can keep hitting return, right? We can keep pointing. We can keep doing our, normal instruction pointer overwrite. Keep sending it to the return opcode we know is a main. Doesn't seem that useful, but it's something we can do, right? Yeah.
So you're sending the return address to the address of the return instruction?
Yes. Right. I could set it to any instruction in main, but we get this interesting functionality when we do it to the return instruction because we keep going up the stack.
And why isn't the correct return address above the last fake one you injected?
Because maybe the old function has a lot of local variables, and there's actually data in between. It could be the correct one, and the program just skips running the old function, right? There's a lot of uncertainty there. But all we know is that we can keep popping up the stack for values we wrote, which might be useful. Any other questions? Yeah.
How can a program defend from something like this?
We talk about that in 1 week. Okay. Anything else? Okay. So that doesn't seem very interesting, but it's something we can do. We can now continue to repeatedly jump to values we wrote on the stack, whether they're useful or not. But the idea that we can keep going up the stack may in itself be useful because we control that memory, right? So let's take it a step farther. I think my Firefox crashed. That's wonderful. Let's see, it definitely did. What's on the next slide? I can just say. So what if instead of going to this return address, we go one instruction right before, right? So let's say we go, I'll do this one, right? The move, okay? So if we now jump to this move instruction, it'll move 0 to EAX, and then eventually do the same thing, return, right? And we can keep doing that. So this is what we refer to as return-oriented programming. We keep jumping to one opcode right before the return. It'll execute that opcode and then hit the return opcode, right? So what we'll do is, say we have our list of overwrites, right? And currently we're just continuously hitting the same return opcode. But maybe we put different values here. Maybe this is 20, 30, 40, right? And all of these correspond to different things. So maybe this one will be move EAX 0, right? And then return, right? So this will jump to here. So what will happen is I'll get the effect of this move, then return, and then we can go to this next one, right? So I can do this move, and then maybe it's compare EAX return, right? And that's what this points to. So I can keep executing different opcodes that are already written in the program right before returns. Okay? Does this make sense?
Yes. How does it know like where the return address is now because you changed the.
Because every time we do return,
Oh,
we pop off the stack. So as long as we still have access to overwrite those stack values from the initial buffer overflow, we can do this. So what we're doing is when we have the buffer overflow, we write our entire exploit script of everywhere we want to jump in the program in the correct order. Okay? This is one of the most confusing topics in the class, like conceptually to understand, but if you get it, it's one of the most widely used exploits in the world. Yes?
If we don't know like the memory addresses beforehand, how can we figure out the return address?
Of code or memory? Because realize that all you need right now is the actual code of the program, and you don't need like the location of your buffer, right? Those are, one is static and one is dynamic.
Oh, so your code memory is in a separate location. So we don't know the locations on the stack.
We don't know where the stack is, but we know where all the code is. Okay. So now we're only referencing code already existing in the program. Realize that if the program's really like does nothing, then this will not work because you don't have places to jump to. So in the example I gave you today in class, I compiled it statically. So all the code fgets needs to run is in the binary, right? So fgets is a huge function actually. You can like do ls-la or something and see the size of the binary. It's big. So fgets has a lot of sub-functions that have returns and opcodes right before the return that we can call. If I did this dynamically, you would not have those return addresses, and you wouldn't be able to do anything useful. But like, okay, fgets reads input. So eventually there has to be a syscall, right? So eventually we can do all these, set up parameters for a syscall, and then jump to the syscall opcode, right? So you can get full whatever execution of what you want. It's making sense. Okay. So now you may be, well, how do we find useful things? And luckily someone has done that for us. Let's see if Firefox has uncrashed. Yes, okay. So we just showed this. You can continuously write the return opcode address and jump to it. So this is a good example. This isn't in the program you're exactly looking at, but this is something that you should be aware of, right? Say we have this code somewhere in the program, right? And we just showed we can hit that return address and continue to return. But pops are exceptionally interesting, right? Because consider pop takes the value off the top of the stack, just like return, right? So if we jump to this first pop, the next 3 values on the stack, which we controlled from the original buffer overflow, we can now move into these registers, right? So we don't need a move command. Move is like, this sucks for us to do return-oriented programming because we can't control this 0, right? We can only move into the register what the program's already doing. But if we do pops, pops take out the stack, which we've corrupted. So we can put any value into these registers using pops instead of moves. Does this make sense? Right. So here, if I, as my first overwrite, instead of 40, let's go through this, right? So instead of 40, I jump to 40B FF8, right? And then I'm hitting this pop, right? So then in my actual code, the values I'm overwriting now will be what I want in R12, what I want in R13, what I want in R14, right? And each one of those, so the first return that gets that code pops this off. And then the pop R12 takes a value from there, R13, R14. And then this will be next gadget, right? And when I say gadget, we refer to things like these as gadgets. This is what's commonly known in the industry, right? So we keep continuing to a gadget. If we get useful things like pops, we just put the parameters on the stack, just like you would do if you had a lot of, parameters in normal programming, right? This is like basically how 32-bit calling convention works. So yeah, now we have an efficient way to control registers if these do exist in the file, right? Questions on that? Yes.
If there's no good commands we can use that, or no good spots that use these registers, then is there any point in having them, or just
and what do you mean? So
if we get these registers, but then there's no opcodes that use them in a meaningful way that we care about near a return or a way that we can jump to.
Are you saying R12, R13 is a little weird, right?
Yeah, what if something didn't use that for the rest of the program.
Yeah, so that's like, these could be useless if we don't have anything to actually do like operations with R12, right? But maybe we set RAX to R12 later on. So we can control R12, now we can control RAX. So that'd be, think about that, right? Look at that one side. So, where is it going with this? But like, okay, so if we have a pop RAX, by the way, then we can instantly control whatever syscall type we're using, right? So depending on the register, it's a lot more important than other ones. So typically you're looking for RAX for syscalls specifically, and then whatever parameters are passed to functions like RDI, RSI, what's it, R8 next, is the order, something like that. So specific type of gadgets we're looking for are called write, where, what. Sometimes it's referred to what, where, depending on if you're using Intel syntax or AT&T because they switch the order stuff. But notice these aren't linear. These are just random things in different locations, right? So it's not like if I call this line, we'll go to this one next. This is self-contained because return ID is at the back. But consider these 4 sets of opcodes, right? If we have these 2 pops, we can now control RSI and RAX, right? Like we showed earlier. We can now put any value into these registers. So we can control registers, pretty important, but we can't write to memory, right? So this is what this allows us to do. We can use RASI as the pointer in memory and set it to the value of RAX. So the idea of write, where, what gadgets are a set of commands that we can use in return-oriented programming to write anywhere in memory. Okay. So say we want to execute a shell and run the command binsh, like we were showing in the shellcode lecture, right? In the shellcode lecture, we used the push command to just write to the stack, and then you can use the stack pointer, or you can pop things into registers to use that, right? But we can't do that here. So instead what we do is we write it to memory with something like this, and then we can use that memory pointer in our syscalls. This makes sense, right? You will need stuff like these for projects. But again, this is cool and all, but how do we make sure the program actually has these? Or how do we find this functionality without digging through the assembly of a 1,000,000 byte program? There's this fun tool people made called RockGadget, which does everything for you. Isn't that convenient? So we're going to learn how to use that real quick. I have it here, I believe. So you're going to need to install this for the next project, but you don't need to demo it today. So all you do is run it, and then give it a binary. We're going to give it the current file I gave you for today's lecture. Let it run for a second. Wow, isn't that a lot? So this gives you basically every possible. Notice it also does it with jump because there's something that's basically the same thing, but it's called jump-oriented programming. But side note, it gives you every possible gadget, right? So this one does some opcodes is this readable? I can make it bigger. Right, so let's actually run it again, and then does anyone have assembly command they want to run? Right, okay, so let's search for pop, right? So pop, what's a register we care about? RAX. So we can just run that through grep. It'll see if that shows up anywhere. I think it does. So suddenly, this tool tells us at this memory location in the fixed code of the program, there is the assembly pop RAX return, right? So now if we do our buffer overflow, we set the instruction pointer to point to here. It will then jump to that location, pop the next value off the stack, which we also control, into RAX and then return. And then we can continue doing this process, and suddenly we have control of this register, right? And this all stems from one gets call. So you imagine if we look for the gadgets for everything we did in our shellcode lecture previously, we can just redo this in a ROC chain And suddenly we don't need any pointers or any memory leaks in our program. All we need is the buffer overflow. And this makes life so much easier. Because the amount of times you get buffer overflows but not memory leaks is probably 90% of the time. Right? Any questions on this? Conceptually? Industry-wise? Yeah?
What binary are you running this on?
I gave a file on Moodle called vuln.c, and if you compile it on your system, it's the same thing. Are you saying the tool or the thing we're testing?
No, you answered it. I'm just confused why there's so much assembly because the program's so short.
Okay, so the program contains all the code for fgets, right? Because I compiled this statically. So I could send this binary to you, and if you don't have the library installed, it'll still run. Turns out every libc function is huge because of all the stuff that goes on in the background, right? If you look at the source code for fgets, it probably does like at least 10 other function calls of all different things, wrappers, so things don't go out of error. And then like it has to do all the file I/O and background kernel stuff, so it deals with that. And the assembly is all for that. Yeah.
So if you had compiled it dynamically, this would...
You would not have it. You'd be screwed, right? But then raises the question, okay, can we jump to the actual libraries for ROP chains?
Yeah.
And we do that later. But that's something else. You need to find out where the library is in memory, right? And you back to your original problem with the buffer. Yeah.
Do you have to like plan out the buffer that you give or like the overflow that you give at the start based on all these addresses like well in advance, or?
So if I do my overwrite, right, I send all the data at once because I'm doing a gets call. I don't know how to execute everything. Something that you can do though, say you want to run some code to do a leak, get some more information, but you only get one buffer overflow and you feel like you're screwed. You can just jump back to main, right? So say I do my initial overflow, I corrupt all this data, and then I do some syscalls, read some data, but I want to write a new exploit based off that data I read. Well, we'll just jump back to main, get the entire stack set up again, and then we'll just redo a buffer overflow. Then we can just continue to do that, right? So technically, you can keep calling it as much as you want, as long as you don't corrupt enough to crash. Anything else? Okay. I don't know how much more material I have, but we can run through an exploit for today and get an example going. So let's live code an exploit here for a ROP chain, right? And then I think for people that want to, ROP-Gadget is the tool that we officially use for this class. But I think PwnTools itself has methods to find gadgets and binaries that aren't dynamically located or relocated. And then if the code is dynamically relocated, if you get like a memory leak of where it is in memory, PwnTools can calculate the offsets for you. So you can actually use PwnTools to find the gadgets you want, but it's a little bit harder and you have to read the docs. Okay, so who wants to write an exploit? Okay, so what would be the first thing we want to do? Okay, I have it set up so the next thing we write will overwrite the return address. What sounds like something we want to do? First, what's our end goal? Who wants to decide what our end goal is? Anyway. Yeah.
We do the system call to get a shell again, or no?
Yeah, okay, so let's make that our end goal. What would be one of the first steps we need to do that?
We have to change, we have to set RAX to 59.
Yes, right. So let's run a ROP-Gadget, right? Give me a second. Okay, and what do we want to search for to find a gadget that does that? Yes?
Either like add RAX or remove RAX.
Is there a smarter one? Yeah, okay, so POP will get it to us, because, so something you could do is you could set RAX to 0, and then add, like, I don't know, 59 times, right? If you also find an increment or a +1, so that could be possible, but this seems like a better solution for now. So we'll let that run, and then meanwhile, I'll prep this so we can do. And then let's just use this gadget, right? We'll add that to our payload later. Okay, so we can set REX to whatever you want. What else do we need? Yeah.
I think we had to set RDI and RSI to 0.
Okay. So what is the gadget we want to search for that?
It could be move or Zor.
Okay. So there's actually this is a good point you bring up. So if we use less gadgets, right, we have to be mindful of how much data we're actually writing. So this program only lets us write 256 bytes in our overflow, and like 16 of those is just to get the return address. So if our ROP chain's not efficient enough, sometimes you won't actually be able to do anything. So using one-liners like XOR to set to 0 instead of, or like move or pop instead of adding 59 times can actually matter. So you do have to be conscious about that. So we said RDI, right? Let's see this one for that. And if not, we could do, okay, it doesn't look like, so we could do pop, and it probably is. Okay, so I'll just take this one. So be aware, this is basically what your script is going to look like for the labs. I'll also show you another functionality of why we use ROP gadget. Actually, I'll do it now, just so we don't forget. So right now I'm setting the flag for, I don't know if you can read it at the bottom, but I'm just setting the binary flag to run for this file. But there's also just -- ROP chain. I think I can put it after, but we'll see. That won't. Okay. Oh, it did. Okay, so ROP gadget has this fun tool that will just write your entire exploit for you, right? So we can manually look for all these pops, which you should be doing in the projects, right? Because you need to learn how this works. So you can manually look for pops yourself and set all the data you want, and look for the right, what, where. I think it's in the right order, right? And this tells you all the gadgets it finds that can do those things. And it tells you the exact syscall numbers it gave. So it gave an RAX and add. The pop is more efficient, like we were talking about, instead of adding 59 times. And then here it gives you gadgets for popping RDI, popping RSI, so you can set it to 0. You're going to need to use the write, what, where. Keep in mind, because what we're going to want to do is write the command we want to run to memory, right? So we want to run binsh. We find a spot in memory we can write to, and then use these gadgets to write the actual string out. And then we can reference it later in the ROP chain as a parameter. Yeah.
Why didn't people who were developing these programs just use like a different register for system calls so that this?
What do you mean different register?
Like avoid these gadgets being found. Possible to stop this from happening.
So are you saying let's have a custom register that can only be okay. Realize syscalls have to be called from the user program. Right. And how are you proposing we do that without the current registers?
Like as you said, like make a custom register just for system calls.
Okay. So there's a custom opcode to invoke syscalls, right? But if we have a custom register, eventually we have to set that register, right? It has to be somewhere in the code. So all it does is add like a layer of obfuscation and not like make it any technically harder. Because eventually the program will have to have that code somewhere. And whether it's hard coded to only allow this value, sure, you could do that. But then you could also, instead of rewriting how syscalls work, you could just set permissions for a file and then implement like a permission thing. So maybe your program only has permissions to read and writes, right? Which is the case in some operating systems. Like Android, every application has to be compiled with set permissions beforehand, and they can't do other things. Okay. So also think that like checks like that, any program that does file I/O of any type, any read write data has to do syscalls. So if you're adding 4 4 extra opcodes to every syscall, the overhead's actually a lot. Any other questions? Yeah.
So you said you could run out of space to do the exploit, but can't you just add another return to where you get the input again?
Yeah, right. We can always jump to main and do that, but maybe consider, what if main isn't just a function like this? What if main is 2,000 lines of code and the registers we previously set get corrupted while main runs? So maybe we set the parameters and just jump straight to the gets and skip the start of main. You have to get creative with it, but in this case, it's pretty easy. Yeah.
Is there a minimum number of bytes required to really start this process? Because
well, you need at least enough to get to return pointer, and then 8 bytes per thing you want to execute. Any data you want to do is at least 8 bytes. For something like a syscall, you probably need at least 40. It's worse than shellcode in terms of compactness. But yeah, something you can see. So RockGadget is very great with this. I don't recommend you do your code like this. You'll get much more if you do it by hand for the project. You can use these gadgets. I highly recommend using the gadgets found by this command, but using this actual script is very bad. It's very inefficient. RockGadget doesn't have any optimization for that. But you can see RockGadget, instead of using the pop we found earlier to set RAX, would rather XOR to 0 and then add 59 times. This will not fit in the current program. Okay, we can't do this. So you have to think for yourself again. But yeah. But all of this is exactly what you want to do. So you can see here we're popping RSI and then setting the place we're going to write in memory for that. We're setting it to the location of the actual data of the program. So remember we said there's certain segments in the ELF structure for global variables, right? We always know we can write there. So if we know that's also in a constant location, we could use that to store bin.sh. So right, think about in the projects, when we have I don't think in the buffer overflow one, but maybe project 3, you will need to write bin.sh to launch a shell somewhere, right? And we give you strategic places in the file to do that. So remember that there are certain locations for writable memory. Okay, and you can see we're popping RAX, right? And then immediately the value after we write is the actual string. So the string is in our ROP chain above the pop, so it gets in that value. Questions? No? Okay. We have 10 minutes left. I don't really have anything more to teach. So unless people want to ask, did I miss anything, Gilbert?
If no one has a question, talk about the project, the presentation requirements, maybe.
Okay. Unless is there any questions about how ROP chains are actually used? Yeah.
So where is the bin.sh string being stored? Is that being stored on the stack?
Yeah. So you see how we're adding the P here is the payload in my script, right? And we're adding all these locations in memory to jump to. This would be the equivalent of if I have a pop RAX and I want to put the value 3 here. Remember how I said the value of what I want, I just put on the stack? I can just write the string to the stack, and it'll pop off the string and put it in that register.
We'll have to do one character at a time, though, right?
So what you can actually see in this code is here we have @data, right?
Okay.
And then here we reference @data plus 8. So what the ROP chain's doing is writing the string 8 bytes at a time.
Okay.
Right? So because everything you pop is 8 bytes, we will have to segment whatever you want to write in 8 bytes, pop it off, write this part, pop it off. And then also consider, even if your string's 8 bytes, you also have to write more to null terminate it. So you might have to write 16 bytes instead of 8 to write an 8 byte string. All right, anything else? Any questions about how ROP chains are used in the wild? Malware. Yes.
Our ROP chains used in the wild and in malware.
So usually when you have buffer overflows, we talked about it's 20% of all bugs right now. You don't have memory leaks, right? Usually when people have, if you're talking actual I don't want to use the term nation state, but nation state exploits, right? And stuff that governments or malicious users do. they'll have like a collection of 5 different bugs that they chain together, right? You may have a buffer overflow somewhere, but you have no idea where anything is in memory, right? What we're doing right now is because security protections are off. This will not work in the wild, right? So maybe you have a buffer overflow, but you can't do anything with it. And then maybe another program has a memory leak, but no buffer overflow, right? So you start collecting bugs like this, and only when you have like 4 or 5 can you actually write a meaningful exploit. And that's when you find like a 0-day in Windows, and you can get into like anyone's computer. It's going to stuff like that, right? But that's also very hard to find. You're not going to be able to do that as a single person unless you're like one of 1,000 security researchers, right? Or you put like years of effort into learning how to do that stuff. But ROP chains are one way to like bypass a lot of security policies. So when we go to shell coding, we'll see shell coding doesn't work when we talk about security policies and what computers do modern day. But ROP code is a way to bypass security policies. Yeah.
Maybe talk about NX real quick.
Okay. So NX stands for not executable, right? So the program can be smart enough, the operating system, to designate certain memory locations as not executable and only like readable data, right? So the location of our program where we write strings for like our welcome message or the congratulations message for the projects, that should not be executable memory. And the program's smart enough to know that. So we'll set a flag, and if the instruction pointer ever jumps there, the program will crash because the kernel will say no. So shell coding, because it's all stack memory, is not executable, right? But ROP chains keeps jumping to actual code in the program, and suddenly a stack exploit bypasses not executable because the actual code you're executing is valid code from the program, right? We'll go more in depth later, but that's one of the ideas behind ROP code. Yes.
Is there any way to get the addresses if it's dynamically compiled?
Yes.
Okay.
We'll find that out. Yeah.
You talked about how there's some methods that OS would use as security features to prevent these kind of exploits. What kind of security features are we looking at?
1 week. 1 week from now, you'll find out. I can like name them if you like know them, but NX, ASLR, PIE, stuff like that. Anything else? Okay. What do you want to say about the presentations?
I guess we can quickly just talk about the requirements for the presentation. So a lot of you have, also like the Campfire room is now open. It's just a room at Campfire. If you want to talk to others about it, you can use that, find teammates, whatever, discuss projects. So like the basic idea, we've talked about it a bit before, but for the project, I want you to choose something and basically do research on it. A lot of people chose embedded things, which in theory is okay, but it might have issues because there are also, we want you to do a couple of things with that, and for those you are going to need code. And for embedded devices, it might be hard to get the code out of. Some of the things are that you actually map out the code base, you either reverse engineer it or read the open source code, whatever you chose to do, and kind of lay out how the code is structured, what individual sections of the code base do, what you need to decide what part of the code you're interested in looking at, and you need to actually like, start reading code and like going into like a bit in detail of what this code is doing, why this is like interesting to you, why this might contain vulnerabilities, and see if you can actually find some vulnerabilities. So for all of this, you actually need to get access to the code. So doing something embedded might pose some challenges. Also in the second half of the semester, we're going to be talking about different dynamic analysis techniques. These include things like fuzzing, symbolic execution, Ghidra scripting, stuff like that. And we also want you to choose at least one of these and also implement it in your project. So all things where you need code and need to be at least able to statically analyze it. And yeah.
That being said, like if you're doing an IoT device and you get stuck getting them like just the code off, that might suck for your presentation. But assuming you have code, if you don't find a 0-day, that's expected. We want to see we'll ask every 2 weeks to see people giving like an honest effort of trying to figure out what the code's doing. Let me put it in perspective. Governments and like large agencies and people have realized this reversing and figuring out how stuff works is a hard process. There are people that will pay you to do research just to figure out how something works, and if you show anything, it's valid. You don't need a bug, just any research is good.
It's going to be my job. after school.
Right. Like I got paid months of work to find out how something worked. 0 bugs, and they're just happy that they have a 2-page PDF on how it like slightly is implemented. Right. That's how the real world is. So as long as you show like gradual, like increased effort throughout the semester of trying to figure out how something's working, maybe ideas of where there's bugs, even if you don't find one, like maybe there's some input functionality that seems a little like wonky, or like you suspect if there is a bug, it could lead to further issues. Like the thing we were talking about earlier, like if there's like say you're doing like a messaging app and they don't like check whatever data you can put as like the username, you can just write whatever you want. That would be something to like post about in your presentation, right? And at the end of the class, we're expecting like a 15-minute to like 20-minute talk, depending on how many people you have, on like what you found, current thoughts, how the code's working, right?
About halfway through the rest of the semester, we're probably also going to be requesting kind of like a write-up or kind of description of where you are at right now, what you've been doing, stuff like that.
Probably a few check-ins, right?
Yeah.
So you don't just do it all last week, because you definitely can't do it all last week. But any questions? Yeah?
I just wanted to say, I guess everyone here has probably taken 320 or 326 where you had a group project, and you were either the person that did a lot of work or the person who didn't. If you are in a group and you're having like problems, I don't know, conflicts, or you're having worries, come see me before you sort of have a big fight. If you have concerns about another teammate, we can talk about how you can approach that. Honestly, like that is work, right? Like good news, when you get to work, like you'll be paired with someone who's also getting paid and isn't really pulling their weight either. So it's a good time to kind of learn how to do that. And if you're the person that's not pulling their weight, like don't do that, right? And I also have to talk to you. I'm like middle management when I do that, right? It's not why I have this job. So anyway, just I'll say that more nicely. Be considerate of your teammates. We all have like balancing priorities. If once you find your teammates, maybe you should exchange schedules and be like, oh, I have a midterm this week. You don't, I haven't gone away on spring break. I'm not. You should coordinate that all ahead of time. That's what professionals do. Everyone has like family stuff to balance. So I don't know, just figure that out. But last thing I'll reinforce, come see me when you think things are going to get bad, right? Before that point.
Should we be looking at like network security in the sense like websites and like the kind of security stuff they're implementing?
So I want you to look at low-level stuff, right? I don't want you to go digging through JavaScript code, because JavaScript isn't really applicable to what you're doing. But let's say you're doing one of those IoT devices and it has a network stack. If you find a way to interact with it or you want to look at it, that's perfectly fine.
Or the Linux kernel TCP stack. That's probably a bit more complex than you'd want, but it's an option.
Like if people want to do complex projects like Linux or Windows kernel stuff or whatever, like modules, drivers, we can like show you how to start.
Browsers, CPU bugs, there are plenty of hard targets that are interesting but take some like time to get started on. We would probably have to adjust the requirements for the project for that group accordingly, but if you're interested in something like that, we can talk about that too.
Yeah. We'd all rather you shoot a little high than a little low. But if you want to do one of the more like ambitious goals and like learn something, we can give you projects we've done in the past or like show you the way to start things. Any other questions? Yeah.
In the shellcode lecture, we ran code that was like on a stack. So were you talking about like executable code sections?
Yeah, so usually on modern computers with defenses, stack memory is not executable. And all shellcode that we wrote last lecture, the upload one, is all on the stack, so none of that would work. But ROP bypasses that by accessing actual executable code that's originally in the program.